Thank you, Julia.
Thank you for the introduction, for the invitation. It would have been nicer to be there, but maybe at some point later in life. Thank you very much for coming. So this is relatively early in the morning for me. So the talk is going to be pretty simple, and I'll start very slow. Hopefully I won't put all of you to sleep, but I don't think I can go any faster too early in the morning. So, well, let's start from the beginning. The pictures, actually, maybe we'll get back to the pictures in the end. I'm sure you guys can recognize at least one of them. Okay, so I wanted to dedicate this talk, which is on cohomology, to Len Evens, who was the person from whom I probably first learned about group cohomology. He was a professor at Northwestern. He passed away earlier this month. And he wrote one of the Bibles for the subject, the cohomology of groups books. And he was actually also the very beginning of the subject that I want to talk about. It's a very interesting person too. And I'll get to Len's main theorem somewhere in the middle of the talk. Let's see, can I scroll actually? Okay, so we'll start from the very, very beginning. What I'm interested in is representation. Representations, let's say first of a finite group. We'll get a little bit more general later on. So I'm going to assume that I'm in the setting when G is a finite group, K is a field, first of arbitrary characteristic, and a representation is just a vector space on which G acts via linear transformation. So if representation is finite dimensional vector space, we can choose coordinates, and then we can equivalently say that there is a map from my group G to the automorphisms of this vector space, which is just GLN n by n invertible matrices. Let me check if I can. Thought there was a pointer here. Can you guys see my mouse when I swirl it around?
Yep.
Okay, so I'll just use that.
Perfect.
Okay, then I'm going to package representations together into a category, which will be the abelian category of representations of G. And ultimately, I'm interested in the case when characteristic is positive. But let me recall the most classical result first in the subject, which holds for zero characteristic, and that's Maschke's theorem. Actually, maybe before we get to Maschke's theorem, I want to point out something about the representation category, which again, everyone is familiar with, but let's look at it from this very, very primitive perspective. If you have vector spaces, then you can do operations on them sort of the way we do operations in a ring. So you can add vector spaces, and then the direct sum is still a representation, still have the action of the group G by a block matrix. You can multiply them. And here we really use that we have a group. So we just take tensor product of two vector spaces over the field, as usual, and then allow group to act multiplicative, to act diagonal. Then there's a unit. One can take one-dimensional trivial representation, and it acts as a tensor unit. So you multiply on the left, on the right, nothing changes. And all these operations are related by the usual associativity and distributivity law. So in a way, we can view this representation category having sort of a ring structure. We can multiply, we can add, there is a unit, and they're all compatible in a nice way. So this makes representations a finite tensor category. I'm not going to write the axioms, but you formalize the way you usually add and multiply, and you get a finite tensor category. And in the case of groups, it's also symmetric, meaning that you can multiply V by W or W by V, and they're naturally isomorphic. So it's a special property which doesn't always hold in more general cases. But the outcome is that we can sort of work with this category as if it were a ring. Okay, now let's get to Maschke's theorem. Maybe I'll tell you about Maschke a little bit. He's my favorite person to talk about because, well, the theorem is so central, but also his career path was interesting, and sort of tells you that even a long time ago, one would not expect the career path in mathematics to be sort of straightforward. And it's not easy, but very, like, sometimes you get where you want to if you persevere. So he was educated in Germany. He's German. He, I think, got his PhD in Göttingen in the 19th century. And then he got a job at a gymnasium, which was a pretty standard thing to do because you had to be Klein or Weierstrass to be professor at the university. Most people would go and teach. But teaching positions, I think, were a little bit more posh than now. After about 6 years of teaching, I think he got a sabbatical. And he went back to Göttingen. I think he worked with Klein there for about a year. And then he was supposed to come back to teaching. And at that point, he understood pretty clearly that as much as he loved teaching, he was a very good teacher, it wasn't satisfactory enough. And he really wanted to have a research position. So he basically made it to be his goal. And to get there, he went back to the university and got a degree in electrical engineering. And then he actually worked, he didn't work, but he had some sort of a practice apprenticeship, something, for about half a year as an engineer. And I think on April 1st, 1890, he sailed off to New York. And he got a job with the New Jersey Winston Electrical Company as an engineer for about 5 months. And then there was an offer that arrived for him to join a little known at that point place as an assistant professor, which was the University of Chicago. And for the rest of his life, which unfortunately didn't last for too long after that, he died relatively young. He was professor at the University of Chicago. He proved some of his famous theorems. So this is the one that we all know. He became very involved with the AMS. He was the vice president of the AMS. And all of this actually learned from his obituary, which was published in the bulletin of the AMS in 1908. So this theorem, I put the formulation of it at the very top, can quote it from the bulletin of the AMS, that every finite group of linear substitutions, blah, 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 is intransitive. It's basically impossible to understand. I mean, you have to unveil all the terms to see what it means in modern language. Now, one can put it in Burnside's modern representation theoretic terminology and say that every group of linear substitutions of finite order is completely reducible, which is already closer to what we would say these days. But I wanted to state it in very simple, like matrix terms, going back to the fact that representation theory is basically just linear algebra. So in terms of linear algebra, Maschke's theorem tells us that if we have a representation of a complex, if we have a complex representation of a finite group, so base field is C, such that when we map G to GLN under this representation, we land in a block matrix, like the one here. We can always change bases to get rid of this matrix B, so just block diagonal. That's all it says. And going back to Burnside terminology, says that if you have a representation of G and a G invariant space, you can always find a G invariant complement. Now we say that representation is simple if it doesn't have proper non-trivial G invariant subspaces. And then Maschke's theorem also means that any complex representation is a direct sum of simples, right? You just prove it by induction, sort of peeling off your simple submodules because you can always find an invariant complement. So this basically tells you that if you want to describe all representations of a finite group over the complex numbers, you just have to describe all the simple representations, and then everything else is direct sum. So describing them up to direct sums, just describing simple representations. And simple representations are also, they're not like out there, they live in the group algebra itself, easy to find, not easy, but you can find them there. So let me remind you about the group algebra. For finite or actually any group, you form a vector space where the basis is given by the elements of the group, and then just extend everything linearly. In particular multiplication, we multiply as in the group and extend linearly. So this becomes an algebra called the group algebra of G. And then instead of studying representations of G, we can just study modules over this algebra. It's exactly the same thing. And then if our field is a field of complex numbers, then as, say, left module, when G acts on the group algebra by left multiplication, we can decompose it as a sum of simple representations by Maschke's theorem, and all the simple representations appear in this sum. So the simple representations of G are just direct summands of this very specific representation on the group algebra. So we know where they all live. Okay, sort of a silly comment. I'm sure you've all seen Maschke's theorem in your first year graduate algebra class or at some point. And the proof is very easy. You basically use the symmetrizing function. And there's one thing in the proof that you always do. You have to divide by the order of G when you sort of average out to find the complement. And it's all fine if you can divide by the order of G if you're over C. But if your field does not have characteristic 0, then division becomes a problem. And that's where Maschke's theorem fails. And in fact, it has a more, it has a stronger version, which I think doesn't make it usually into the standard textbooks, that it actually holds if and only if P does not divide the order of G. So as soon as you are in what's called the modular case, when P divides the order of G, then Maschke's theorem completely fails. Like pick any representation, like any group with this condition, then representations are not reducible. So it's if and only if condition. Okay, so I'm interested precisely in the case when it does fail, because it makes things really interesting. And the first such case is characteristic P for a finite group. Of course, when you're in characteristic P, all sorts of funny things happen. Like, for example, we have this freshman calculus rule. So some things become easier, but some things become harder. So in particular, Maschke's theorem fails. And it's very easy to see that it fails. Like you take a cyclic group of order P and try to look, you immediately figure out that the only simple representation is the trivial representation of dimension 1. So one-dimensional trivial representation. On the other hand, indecomposable representations, the ones which don't split as direct sums anymore, are in one-to-one correspondence with Jordan blocks of size from 1 to P. That's a relatively simple exercise, which I'm sure if you've ever worked with characteristic P, you've done. And then one sees that, well, there is one simple representation, but P indecomposable representations, and there's no way you can have Maschke's theorem here. So it just fails right away. It was the only point I wanted to make. Okay, so to finish off with characteristic 0, one can sort of draw this diagram. If you look at representation category of a finite group over a field K, there are two very different cases. Characteristic 0 case, or actually more generally the case when characteristic does not divide the order of the group. Then everything can be described up to direct sums by irreducible or simple representations. This is given by irreducible characters. And this goes back to, the whole theory goes back to 4 founding fathers of representation theory. It's Frobenius, Schur, Burnside, and Brouwer. And the history of the subject is very nicely described in Charlie Curtis's book, Pioneers of Representation Theory. All the mathematics and everything that happened around mathematics on that. And then you have characteristic P, where you still have character theory. And this actually goes back to Richard Brouwer as well, so one of these 4 people. But it's not enough. Even if you can describe all irreducible representations, irreducible characters, you're still sort of stuck describing the rest because things don't split as direct sums of these irreducible representations. And to describe all of them, you need to allow for other techniques, other invariants, and need other tools. Okay, Now I'm going to say something that I'm sure everyone here knows, but anyway. So I want to generalize the situation, go from group algebras to Hopf algebras. And basically, I'm going to tell you what a Hopf algebra is. Just don't kick me out just because of that. So for the group algebra, which is a vector space generated by the elements of G, what do we have? We have multiplication in there. So it's a map from 2 copies of the group algebra to 1 copy of the group algebra. And it's just given by multiplication in the group. We also have the diagonal map. So it goes in the opposite direction. And this is the map that's important for the tensor product of 2 representations. To define the action of the group on the tensor product, we use this diagonal map because we act diagonally. And there is an inverse map. And the inverse map sort of relates these 2 multiplications, multiplication and diagonal map nicely. Okay, so the Hopf algebra is vector space over a given field K. So we always fix the field K, which sort of mimics this property. So we have a product, a map from 2 copies of U to U. When I write tensor product, I always mean over the field K, just as vector spaces. We have the co-product, sort of the generalization of diagonal map. We have the co-inverse or antipod, which mimics the inverse in the group. And then we also have unit and co-unit. So this U is an augmented algebra, meaning that there is a map to K, and it's an algebra over K, meaning there is a map from K. And then one can write myriad of diagrams to relate all of these operations to make the thing into a Hopf algebra. And it's finite dimensional simply if the dimension of U as a vector space is finite. We can again consider a representation category of U. So in the same way as before, we can allow U to act on vector spaces. And then it will also act on sums. We can consider products when we take tensor product over K and use the co-product to define the action, so the analog of the diagonal action. And again, we can sort of view the representation category as a new kind of a ring. The only thing is that in general, it's not going to be symmetric. So this requires some special property of the Hopf algebra U for this category to be symmetric, to be able to switch in the product to 2 vector spaces when we take the tensor product. So this actually brings some interesting things into the theory. Okay, examples of Hopf algebras. I'm not going to give a comprehensive list, of course. Hopf algebras are ubiquitous and show up all over the place. I'll just mention the ones about which I can say something and which are relevant to the theory I'm trying to describe. So of course, for a finite group, or actually any group, the group algebra is a Hopf algebra, and it's the corresponding category is symmetric. Universal enveloping algebra of Lie algebra is a Hopf algebra. In positive characteristic, universal enveloping algebra has a finite dimensional sort of companion called the restricted enveloping algebra. It's a finite Hopf quotient of the universal enveloping algebra. So these are the ones, this is the one that we'll be interested in particular. More generally, actually, in positive characteristic, we have finite group schemes over the field K. So these ones, I'll talk about them later in more algebraic terms. But again, basically, a group scheme is something that has coordinate algebra or algebra of regular functions. That's going to be Hopf algebra. If the group scheme is finite, it's going to be finite dimensional. So we can dualize it linearly and get another Hopf algebra called the group algebra of this finite group scheme. And that thing is a finite dimensional co-commutative Hopf algebra. And it actually incorporates examples 1 and 3 in it. Even more generally, one can consider a finite supergroup scheme. So basically, it's going to be a scheme in the category of super vector spaces. And then one does the same thing, looking at the algebra functions, dualizing, and it's going to be a Hopf superalgebra. Should make a disclaimer that this is a lie, as I'm sure, especially people here understand very well, that if you define the Hopf algebra in the category of supervector spaces, then it's not going to be actually an honest Hopf algebra. It's only going to be Hopf algebra in that category. But basically everything I'm going to say is going to work for these things. It's just you can't apply results for Hopf algebras. You have to keep in mind that they're Hopf algebras in different categories. And this actually becomes interesting in both characteristic 0 and characteristic P, even though in characteristic 0, you don't actually get a lot of new things besides finite groups, except that you do get exterior algebras now as part of the examples. Moving to complex numbers, we have quantized enveloping algebras or quantum groups. And when they are at roots of unity, we get, again, the small finite dimensional counterparts, which are small quantum groups. These are finite dimensional Hopf quotients of quantized enveloping algebras. Have any questions so far? Probably not. I'm sure that most of you can talk about these things way better than I do. But questions are always welcome, and feel free to interrupt me. Okay, so in all these examples, usually representation category is not semi-simple. Moreover, it's not even not semi-simple, it's what's called wild. I won't give a definition, but basically it does have a precise mathematical definition, but basically it says that like classifying representations up to direct sums, it's more or less hopeless. There are too many of them, and one can say precisely what it means. The example of a cyclic group is special because even though that was not semi-simple, we can still classify indecomposable representations by Jordan blocks, but it's very special. Like if you move to if you take two copies of a cyclic group in characteristic at least 3, so this is a group of order 9, then you cannot classify representations up to direct sums in a meaningful way. There are just too many of them. And in fact, there are like open conjectures about representation theory of this group, which you can solve. And in particular, you can have a computer solve them. You can't check them by hand because there are too many representations. So what does one do? Well, one can try to find useful invariants to sort of put representations at least in some sort of reasonable groups. And related to this, one can try to relax the problem. So maybe we are asking too much. So there are too many representations up to direct sums. So maybe we shouldn't be looking at them up to direct sums. Maybe we should be looking at them up to like other operations. And motivation for this actually comes from topology, because topologists have been doing this for a while, formally for like almost 40 years, but informally for longer. And at some point, the ideas from topology sort of made their way to representation theory, and people started looking at representations somewhat differently. And there are some classification questions and answers actually showed up. And I'll try to get to talking about them a little bit. Okay, now my talk was supposed to be about cohomology, so let's get to cohomology. In a very primitive way, what is the situation that we have? So we know that representations don't split. Mashke's theorem doesn't hold. You can have a G invariant subspace. I'm going to be talking about the group G sometimes, but all of this works for any finite dimensional Hopf algebra until it doesn't. So you can have a representation V and then a subspace, G invariant subspace. And what happens is that it doesn't split off. So if you take a quotient, let's call it W prime, then V is not going to be a sum of V of W and W prime. Right? So we get an extension or a short exact sequence, which does not split. And we can have tons of them. And basically, this is what we would more or less like to classify if you want to classify representations. Not only simple ones, but also how they fit together using extensions. Another way to look at cohomology is, well, we want to look at invariance. Well, we can just look at invariance first. So U acts on this vector space V, take invariance, that's an invariant. Turns out that in positive characteristic, again, when we don't have the splitting property, we have not just invariance, we have a whole integer sequence of derived invariants. So this is not an exact functor, they are derived functors. And both of these approaches, sort of points of view, lead to cohomology of our Hopf algebra with coefficients in a vector space in which it acts. And again, this goes back to topology and the work of Eilenberg and Steinrod sort of brought it into the algebraic setting. Okay, I'm going to try to be slightly more formal. Again, these are basic things. So we can define cohomology just looking at extensions. Extension of length 1, this is something that involves 3 vector spaces, is just vector space, an invariant subspace, and a quotient. One can sort of put them together, sort of splice them to get extensions of length n or I, where the length of the extension is the number of the intermediate vector spaces, and an extension is just a long exact sequence. That's all. Now, it turns out that we can package them together into an abelian group. So there's a little bit of shenanigan involved. We have to define equivalence classes. We have to say how to add, but this is all formal. And putting them all together, we get the extension group of length I. Again, I is just the number of intermediate things from V to W. So this is an abelian group. And in a special case, when we put the trivial module on both ends, we get extensions from K to K. And this is called the I's cohomology group with coefficients in K. Looking at cohomology by extensions, it's very easy to define products. So it becomes a graded space, vector space if you just add all extensions groups together, but we can multiply them. And I think usually you first learn about multiplication cohomology by a cup product, but another product I think is much more visual. So basically what you do, you take an extension from here of length I, you can take an extension from here of length j, you switch the order, you put them next to each other, then you identify the ends, you just need to have the ends to be the same, and then you kick it out. And you go directly from here all the way to here. And you get an extension of length I plus j. And actually you can do it whenever the second argument and the first argument are the same. You can always do that, identify them and go through. So another product is just splicing extensions. It's very, very explicit. And this makes cohomology, which is just a graded vector space of all extensions from K to K, into algebra, graded algebra. And one of the first results about this is due to Hochschild, who proved that this is a graded commutative algebra. This actually has a very neat proof, which just uses the fact that there is another description of this multiplicative structure, which is a cup product. And whenever you have 2 different products on graded algebra, which are somewhat compatible, then you can conclude that first of all, products are the same, but also they're both commutative, called the Ekman-Hilton argument. And also, if you look at cohomology with coefficients in a vector space V, then this becomes a module over this cohomology algebra with coefficients in trivial vectors in trivial representation. In the same way, you just splice them together. Like if you put them together, you'll see that in the middle, you'll still have K and K. So you can still do that. Okay, outcome. So first, actually, I want to change my category a little bit. So what I want to do is I want to measure how non-semi-simple representation category is. So I want to adjust it and work with a triangulated category instead in the following way. Let me do it informally first. So recall that in the semi-simple case, we found all simple modules as direct summands of the group algebra. So we know that if that happens, if we're semi-simple, then if we look at all direct summands of the group algebra and close on the direct sums, we get the entire category. So to measure how non-semi-simple our category is, we're going to do the following thing. We take the subcategory of representations of U, where we take all direct summands of U and close on the direct sums. And of course, this is just the subcategory of all projective U modules. Okay. And then we mod it up. This is slightly informal because I'm sort of in the middle between, I mean, it's not clear what I mean by modding out, but let's take this informal definition. I'll give the formal definition in a minute. And the result is the stable category of U. So we sort of stabilized our representation category this way. And of course, it sort of relates to topological notions and constructions to stable homotopy theory. This is where the name comes from. Formally, we do the following thing. So the stable category is the category whose objects are still representations of U, but we change the morphisms. The morphisms in this category are the following things. We take morphisms in the original representation category, and we mod out morphisms which factor through a projective module. And effectively, what happens is that we kill all projective modules in this new thing. Any questions? Actually, let me. Oh, great. Okay, I can open the chat, but I'm not going to understand the thing in there. So maybe I won't even try.
Oh yeah, but it wasn't the question. It was a mistake.
It's okay. Yeah, I didn't realize when I asked you to tell me about the chat, I should have mentioned that. I need translation as well.
No, yeah, it was just a mistake.
So this is the stable category, our favorite category to work with. So here is just a reminder that we at least think about it as a representation category where we mod out the projective objects. Just by construction, at least by this informal construction, if the representation category is semi-simple, like group algebra of a finite group over the complex numbers, then the stable category is trivial. That's basically Maschke's theorem plus that fact that all simple modules show up as direct summands of U. So okay, that's Artin-Wedderburn theorem. Basically, this says that in the semi-simple case, projective modules are simple. Indecomposable projective modules are simple modules. So in the semi-simple case, we don't have any category to study. One can view this from the algebraic geometry point of view, if this is something that like closer to your heart. So this category also is equivalent, I shouldn't have said equal, it's equivalent to the singularity category of U. And now it's formal. We take the bounded direct category of U, that's a triangulated category, and we mod out the category of perfect complexes. The notation, I believe, was introduced by Orlov, although this goes back, way back to very famous unpublished manuscript by Buchweiz, which I think is still unpublished, even though it sort of exists on the web, where this construction first showed up and where it was first proven that these two things are the same, where you just take your abelian category and mod out projective objects, or if you actually do it formally in the derived setting. So in algebraic geometry for commutative algebra or scheme, this is a singularity category, which sort of measures in the derived way how non-smooth your scheme is. So in our representation theory context, the analog is that smoothness is sort of interpreted as semi-simplicity. And the same quotient measures how non-semi-simple our algebra is. Now this category inherits all the operations that we saw in the representation category. You can take sums, you can take products, you can have unit, you can have the unit, the trivial representation, but it also has homological operations, syzygies and extensions. And I'll mention syzygy in a minute, but extensions are just extensions. Now, finite dimensional Hopf algebra is always what's called a Frobenius algebra, which basically means that projective objects are the same as injectives, or projective modules are the same as injective modules. And this fact always tells you that the stable category is a tensor triangulated category. So all those things I was sort of saying about adding and multiplying, and also now these homological operations, they have very formal meaning. It has a triangulated structure, it has a tensor structure, which is the same as in the representation category, and they're nicely compatible. Okay, and one thing I want to mention from the triangulated structure is the shift. So in a triangulated category, we have triangles, and they just correspond to extensions in the abelian setting, and we have shifts. So this is something like in the derived category, just moving your complex one step left or right, depending on the agreement. In this setting, in the stable category, shift is given by the syzygy. Let me define it. So if you have a representation of U, we can put this representation V into its injective whole, so the minimal injective module that contains it, and then take the co-kernel. And this is the shift in this category, the syzygy of V. And this is what's going to be sort of part of the fundamental structure of the stable module of the stable category. Now with this shift, we can consider graded spaces of morphisms, which is usually what's done in a triangulated category, the home star. And this is where we take a direct sum of all morphism spaces with all the shifts. And this is basically X groups. I didn't put, so these are X groups over U, so there should be U here. Except that we also have the negative ones. We have all the positive ones, which we define, but we also have the negative X groups, so this becomes what's called Tate cohomology. Okay, now what we have is the following thing. We have now cohomology algebra, H star of UK or X groups, and it acts on the category, on the stable category. And it just acts by acting on these graded home spaces by unit product, as I described. So graded home spaces are X groups, and we have cohomology acting on X groups. By definition, they act on the category. Okay, so sort of the moral of this is that by looking at cohomology and looking at how it acts, we now sort of replace is not the right word, but we can study our initial action, which is the action of a finite group or Hopf algebra, highly non-commutative often, on vector spaces by now acting with this graded commutative algebra, so basically commutative algebra on the category, on the stable category. So we are replacing the non-commutative actions with this commutative actions or modules over commutative algebra, except that now we have it acting on the category instead of a vector space, but you have to lose something. But now we can use various, lots of stuff that comes from commutative algebra and algebraic geometry, all the tools that are developed there for the action of this graded commutative algebra, H star of UK. So that's sort of the basic idea of what happens here. And again, in the semi-simple case, because, I should have said it, in the semi-simple case, this cohomology algebra is trivial. So first, you already know everything up to direct sums, and these methods don't give you anything. So we're really interested in the non-semi-simple case. Okay, now what can one actually do? I'll list a few things which I'll probably explain some of them, what one tries doing. So one thing that I've been very interested in is classifying what's called tensor ideals in the stable category. So if we pretend that we view this stable category as a ring, sort of, so we can add objects, multiply objects, and they satisfy various compatibility properties. We can define what an ideal is. We can define what the prime ideal is. We can actually define what the spectrum is of this category. And just as a spectrum of a ring, it's going to reflect quite a bit, not everything, but quite a bit about this category. We can ask what it is. This is relevant to trying to classify ideals. Trying to answer, to relate to what I stated in terms of classifying things not up to direct sums, but more coarsely. So in this category, we can classify representations up to all the operations which are allowed there. So it's going to be sums, taking tensor products, taking summands, also extensions and syzygies. So we look at all the natural operations we are doing in this stable category, and we try to classify representations up to those operations. This turns out to be equivalent to classifying tensor ideals. Mentioned the spectrum. This was actually a construction introduced by Paul Ballmer in something like 2005. And the way it's usually done is one tries to construct a support theory in this setting. So for any representation in stable category, to any representation, you associate a geometric invariant, the support, which lives in the projective spectrum of the cohomology algebra. Cohomology is a graded ring, so one can look at a fine spectrum, one can look at the projective spectrum, just the set of all homogeneous ideals. Okay, now I finally get to the main point of my talk. If you want to use algebra geometric methods, then one thing we would really like to know about this cohomology algebra is that it's nice, right? So we want to study modules over this algebra, study various invariants, look at the projective spectrum. We'd like to know it's not some crazy thing. And the first thing, we already know it's commutative. Fine, that's very useful. We'd like to know it's finitely generated. And in fact, we need to know a little bit more. And nowadays I think it's called satisfying the finite generation property, even though there are various other names for it in the literature. And it's the following condition. First, it's just a finitely generated K algebra, the cohomology algebra for K, but we are interested in the action of this algebra. So the other condition we need is that for any finite dimensional representation of our Hopf algebra V, this action by another product makes the cohomology with coefficients in V a finite module of the cohomology algebra. So two conditions, they're very closely intertwined. It's actually a very interesting question whether you can have one without the other. It does happen in Hochschild cohomology for non-Hopf algebras. I don't think there are known cases. I'm pretty sure, yeah, I'm absolutely sure. There are no known cases for Hopf algebras when one is satisfied without the other. But it's also not a formal thing. I mean, if you prove FG1, you still have to prove FG2, at least in my experience. Okay, now the first person who actually realized the importance of the second condition was Len Evens, and he proved finite generation property for finite groups. So both FG1 and FG2. At exactly the same time, this was proven by Boris Venkov, topologist, I think, from St. Petersburg. But the proofs of Evans and Venkov were completely different. So Venkov, again, got his inspiration from topology, and his proof is very topological. He looks at the classifying space for G and uses what's called the normalization technique in finite groups or topology when he embeds this thing into something big for unitary group and then proves it there. His proof doesn't do anything for modules, and it can't actually, as far as I know. Evans does a very algebraic proof. And in fact, it's the techniques he also developed when proving this theorem, which became very, very useful and which we still use when we try to prove finite generation in other contexts. And one of them is what's called Evans lemma, which is the name that I actually learned from Antoine Touzet at some point, and we now started using the name in papers. Okay, so I'm going to list some things which are known, and I just have to apologize. It's not an exhaustive list. There are tons of results, and I'm probably not aware even of some of them, but I'm going to list some. Okay, so for finite groups, it was Evans and Venkov and Golod, who I mentioned before that, he proved the FG1 for P groups, also actually from St. Petersburg. Then Friedlander and Partial got interested in this for restricted Lie algebras, and they were interested in like geometric applications, so they proved finite generation for restricted Lie algebras in 1987. Then Ginsburg and Kummer moved this to characteristic 0 and proved it for small quantum groups with a restriction of the parameter. Then Bendel, Nakano, Partial, Pillen removed the restriction of the parameter by very explicit calculations. Maybe the most famous theorem in the subject is the one by Friedlander and Suslin, who proved it for all finite group schemes in 1997. Then in a joint work with Masnak, Schellenberg, and Witherspoon, we first tried to apply this to like Nichols algebras and extended Ginsburg and Kummer result to a certain class of finite dimensional pointed Hopf algebras, but there were very big restrictions on the parameter. Maybe I'll mention this, or maybe not at the end. Chris Drupieski proved this for finite supergroup schemes, which was quite a surprising thing. That was an open question for what, like almost 20 years after Friedlander-Suslin result. And you would think that if you just add the Z2 grading, it shouldn't be that hard. It turned out to be really, really hard. And then there is a very cool result of Stefan and Wei on 12-dimensional Fomin-Kirillov algebras, where they, I think, almost compute cohomology. Okay, Fomin-Kirillov algebras, not quite Hopf algebras, but very close. You can bosonize them and still compute cohomology. Going further, so there's very recent work by Friedlander, Negron, and Negron on Dringfield doubles of finite group schemes. And then in a very long manuscript with Nichols and Ivan and Sarah Witherspoon, we proved this conjecture for pointed Hopf algebras of diagonal type with abelian groups of group-like elements. It was a very exciting, I think, 7-year-long project, which is probably sort of kind of getting finished. I'm really proud of that. The last thing I want to mention is that I'm working with Chris Negron, again on geometric applications, and we found a different way of proving this finite generation for several classes I mentioned before, restricted Lie algebras and small quantum groups via causal duality that we established for some special Hopf algebras. Finally, the question is wide open in general. There is a conjecture by Etingof and Ostrik from 2004, even though it was sort of in the air in Friedlander-Susin paper in 97, it was sort of mentioned as a question for Hopf algebras. Anyway, Etingof and Ostrik are the first ones who actually put it in writing. And the conjecture is that for any finite tensor category, cohomology algebra is finite, satisfies the finite generation property. It's wide open. I don't think anyone has any idea what to do at this point, but we're making progress on using a lot of work that people do in related areas. In particular, in the work with Nichols and Ivan and Sarah, we use the full force of classification results on Nichols algebras of diagonal type to get to the finite generation. Guillermo, how much time do I have? Do you want me to stop?
No, you have like 15 minutes more because we started late.
I'll probably have to finish at 10 because I do have a lecture to give after that back here. Okay, I'll go on to
okay.
So I wanted to mention applications. And then once you go to applications, I mean, proven finite generation property is the first step. You really want this to be able to do anything in, like to bring in tools from commutative algebra. You want this finite generation property. But it's not a smooth sailing after that. There are various hard questions that you encounter if you want to construct, if you want to use like the geometric tools. So here you have to specify what you work with. And I want to talk a little bit first about the case of finite group schemes. So I sort of defined what they were from geometric perspective, but basically finite group schemes are the category of finite group schemes or supergroup schemes, equivalent to a category of finite dimensional co-commutative Hopf algebras by going from a group scheme to its group algebra. And the important condition here is co-commutative. So the co-product satisfies the co-commutativity property. And in particular, the category we look at here is symmetric. And this includes finite groups, restricted enveloping algebras, for Lie superalgebras, finite group schemes in general. Okay. Now we have the finite generation, and cohomology algebra acts on the stable category, and then sort of answering some of the questions, actually all of the questions I stated before, geometric questions about the structure of the stable category, one can formulate the following theorem, that the cohomology algebra stratifies the stable category. It's a very short formulation, probably tells you absolutely nothing. So because I didn't define what stratifies mean, but it tells you quite a bit about the category. And let me try to describe a little bit what it does mean. So using the action of the cohomology algebra on the stable category, one can associate to any representation the geometric invariant called the support. And in fact, this is the support that I'm sure you've seen in the algebraic geometry setting, like for sheaves, you have a sheaf over a scheme, and then the support is, you can define it by looking at specialization at every point and seeing whether it vanishes or not, or via annihilators. So it's the usual support in commutative algebra. And we can define it because now we sort of moved everything from representations of G to just modules over this graded commutative algebra, which is a cohomology algebra. So now we can define what support is. But turns out that it remembers quite a bit about the original category. Specifically, it establishes one-to-one correspondence between tensor ideals in the stable category, where tensor ideal is a subcategory which is closed under all the operations we can do there: extensions, syzygies, direct summons, and tensor. And on the right, you get subsets in this projectivized scheme, the project cohomology, closed under specialization. Closed under specialization means that if you have any point, you have the closure of that point. Or these are all the sets which are unions of closed sets. And the correspondence just given by support. You start with the tensor ideal and you take the union of supports of all the objects in there, or you start with a set and you take the subcategory with all which consists of all the objects with support inside that set. So some things are easy to show, that it's not hard to show that this is well defined, but showing its one-to-one correspondence requires some actually intricate knowledge about your category. And this is part of this stratification theorem. Stratification theorem is slightly stronger. Of course, this wasn't like built on an empty ground. This has lots of precursors, and motivation comes from stable homotopy theory, where classification result was established for stable homotopy category, but given as Hopkins and Smith. There are results in commutative algebra by Hopkins and Newman, and algebraic geometry in Thomason, which is sort of the same flavor, but very different proofs. This can be put in like abstractly in the setting of tensor triangular geometry produced by Balmer, and then the correspondence, the one-to-one correspondence for the stable category can be recast as saying that the spectrum of that category is just the proj of cohomology. Okay, one can prove an analogous theorem for supergroup schemes, but in somehow once you move into Z2 graded vector spaces, things become different. We can only prove it so far for unipotent things. Unipotent just means that your algebra is sort of local, but not in general. And I wanted to talk about non-commutative complete intersections. I probably won't. Just want to quickly mention the work we're doing with Chris Negron, where we consider in general what we call the non-commutative complete intersection. It's some sort of it's a finite-dimensional Hopf algebra, which is a deformation of a smooth infinite dimensional Hopf algebra. Our main example is a quantum group. And it turns out that various things can be proven just using that condition, in particular finite generation. And so new proof of finite generation using causal duality covers like small quantum groups, quantized enveloping algebras for barrels, quantum linear planes, even though cohomology there is known explicitly. And one last thing I wanted to mention is that that approach, I believe, also covers the work that we did with Masnek and Schoenberg and Witherspoon about 10 years ago for Nichols algebras, but you can also bosonize them, the Hopf algebras, to show finite generation there as well. It does not cover at all this new work with Ivan and Nicholas and Sarah, because in general, Nichols algebras will not be smooth deformations, will not be what we call integrable, whereas the algebras that we consider there, when we put this big restriction on the parameters, they are smooth deformations. So sort of indicates the difference that restrictions on the parameters, like structural difference that restriction on the parameters give you. And one last thing I wanted to mention is the tensor product property. So this was actually the motivation for everything for what we started doing with Chris. In this support business, the way it's defined, the way support theory is defined by the action of cohomology, actually the action of cohomology, if you think about it, it basically forgets about the tensor structure. Even the cohomology algebra, you can have two different Hopf algebras, which are isomorphic as augmented algebras with totally different coproduct, they'll have the same cohomology. So a priori, cohomology doesn't remember the tensor structure. But it turns out that very often, even though you define support via cohomology, which doesn't remember the tensor structure, the support satisfies this what's called tensor product property, that the support of tensor product of two objects is the intersection of support. This is known in various cases, like finite group schemes, for example. Usually it's difficult to prove because, again, it's sort of unnatural for the way we define support. It's an open question. I'm going to attribute it to Ostrik from his 98 paper, even though he didn't explicitly state it as a conjecture, but it's sort of there, that it's true for small quantum groups, open. And this is what we're really interested in, looking at this integrable Hopf algebras. So far, we've been able to prove it for quantized enveloping algebras for barrels in type A. I think I'm done. Thank you.
Thank you. Okay,
They
so
stop sharing the screen.
no, we still can see your screen. Are there any questions? I do have a question. So what you said something about these smooth deformations and Nichols algebras coprime with 210.
Mhm.
Can you say a little bit more about that?
So I think Ivan actually is the best person to tell you about that. But basically the idea is that we want a covering algebra, right? So you have your Nichols algebra. So there is an infinite dimension. So very often there is an infinite dimensional Nichols infinite dimensional algebra where you mod out the relations to get to your finite dimensional Nichols algebra. And so you sort of have a covering. And that's not always the case. Like I think it's always the case in the Cartan case, but not otherwise. But when you do have this, then this is going to play the role of a smooth deformation. So basically what you want a covering algebra, which is smooth, where by smooth, I mean finite global dimension.
Okay. And in the other cases, I mean, when it's not coprime to 210, you don't know if you don't know the global dimension or you know it's infinite.
I think sometimes it just doesn't exist. This is what I learned from Ivan a few years ago, which sort of showed, it really showed why methods that we used in 2010 didn't apply, because there are explicit examples when you don't have such a covering algebra.
Okay.
You have an algebra that covers it, but in that algebra you need some nilpotent elements.
Yes,
I guess this is one of them.
So it's not going to be of finite global dimension.
Yeah.
Okay.
So basically, I guess we're trying to mimic the situation when you have your universal envelopment algebra. Well, I don't know. Do you guys like quantum groups better? Like you have your quantized universal envelopment algebra, you mod out your standard relations, the ELF powers of your generators to get to the small quantum group, right? And this the big one has finite global dimension, so it's smooth in this non-commutative sense. And then there are examples when it doesn't happen, when your parameters, the order of the parameters is not coprime to 2010.
Okay. Thank you. Are there more questions?
Yeah, me. Hi, Julia. Very nice talk. I have a question about the spectrum of the stable category. You say something about, I don't remember if it was a general case or not. You show it in the last theorem about the small quantum group on the Borel. And before that, you mentioned a theorem, but I don't remember for which Hopf algebra.
Okay, so the question is, what is the theorem? What is the spectrum?
No, what is the theorem? Because I'm interested
so the theorem, there is a general theorem in the co-commutative case. If you have a finite dimensional co-commutative Hopf algebra, then the spectrum is always the proj of cohomology.
And what about another families of Hopf algebra, say commutative, coordinate rings of?
Oh, yes. Okay, for the commutative ones, so for the commutative ones, I think this would be, they're going to be complete intersections. And this is covered by the work of Abramov and Buchweiz. So this was sort of the motivation for what we were trying to do for non-commutative complete intersections. And there, things are also known. So once you move to commutative algebras, you can actually say much more. So usually people don't assume, you don't need to assume Hopf algebras. So they can do things for complete intersections which don't have the Hopf structure, much more general class. But if you specify the Hopf algebras, I'm pretty sure, yeah, it's still true. I think it becomes much easier thing to show.
Okay, and for non-commutative
Also showing that
Hopf-
cohomology is finitely generated is easy.
yeah. But for non-commutative Hopf algebra sake, there are very few results. That's true?
Yes, that's true. So, we I think are able to show. I put the 21 as the year there because it's
This is like a future
probably
research
not going to be
something.
finished this month. We hope that we can show. I mean, I'm pretty sure we can show that for UQ of B for SLM, we can compute it. And the problem is usually this tensor product thing.
Okay.
So once your things are non-commutative, non-co-commutative, doing anything with the tensor product, like the techniques that we know, they just don't work. And I've been thinking about this problem. Like we started thinking about it with Sarah Witherspoon, I don't know, like 15 years ago. We have some results for quantum linear planes, special quantum linear planes for special orders on the parameters, where we were able to prove that. But yeah, it just seems mind-boggling.
Yeah, thank you very much.
Okay, more
I
questions?
usually ask a question about the pictures, so I put pictures in my
Is the
slides.
Concagua, isn't it?
On the left, yes.
Yeah. On the left, yeah.
Yeah. You guys probably could guess what's on the right. So it's Mount Rainier. It's my home state mountain. It's the highest mountain in Washington. And the picture on the right, I actually took myself, which I can say about the picture on the left. The picture on the left, I think is, I don't know, maybe from a drone. Sort of too far above.
Or maybe an airplane. I mean, when you fly from Córdoba to Chile, you'll pass like very close to,
you
to
see
the peak. Okay, so I will stop the recording now.